Good morning. Let us start. So we start with choosing the time for the test, number one, and I'm happy to say that it seems very clear and convergent. There's huge support for 13th of April, and the differences are just details. So my proposal is this one. And obviously, nobody will have any classes during that time. And now, if anybody is really in trouble with that time, please shout now. And really does not mean that I have to visit my friends or something. I mean, something really serious, yeah? Like medical treatment starting on Sunday afternoon and ending on Monday or something like that. If nobody shouts, then many thanks. Yeah. And this is the time of the first test. Yeah. I will organize that it will be open for you. As I said last time, it is not mandatory to do it. Yeah, you don't need to do it, and you cannot fail it. Whatever score you get, it's fine. But of course, you lose some points from your final score if you don't do or do it badly. And also, I promised last time to somebody that I will give some more information what will be in the test. So it is mostly about understanding. It's not about solving any kind of difficult problems, not at all. So most questions are something like this. Okay, which of the following is correct? And then it is said that, well, let's say standard uncertainty is an uncertainty which has been obtained by a standardized method. Is this correct or not? Not really. Yeah. The word standard does not mean standard. Okay. Standard uncertainty is an uncertainty which has coverage probability 100%. Is that correct? No, yeah. And so on and so forth. Yeah, and you may need to do some very small calculations. For example, there might be something that, okay, this is the absolute uncertainty of this kind of thing. Yeah. Is this now correct? Let's say it is given that, okay, the combined standard uncertainty of this measurement value is here, uncertainty is here. Which of the following is correct? And now I ask, okay, the relative expanded uncertainty is this. What that means? From the absolute combined standard uncertainty, you have to be able to calculate the K2 or whatever the K expanded uncertainty. And then you have to be able to divide by the measured value so that you get the relative uncertainty. So you may need to do some multiplication, division, adding, subtracting operations, but no big calculations. I don't think you need Excel for that, actually, but you are allowed to use Excel. And also, this test is without materials. You will have to click on some honesty declaration, as it is called there. So you are not allowed to use any materials. I cannot really check that in any way because I'm not running around the dormitory rooms and opening doors and looking how you are doing the test. So I count that you are all honest. And most importantly, please read very, very carefully what is written. Sometimes there are different options, which is correct, and they differ only in small nuances. So that if you just superficially look, you might even not see what is the difference between options D and E, for example. There are always some difference. And also, let me warn you that most of those ticking things may have one or more correct answers. Sometimes it might be given how many correct answers there are. Sometimes it might not be given. You will simply say, okay, there are a number of options. Maybe one is correct, maybe two, maybe three. It's for you to figure out. Any questions? can check. Depending on how you count, either 3 or 6, but some question has like different types of, how do I put it, different like subsections or sub things. But in any case, not so many. Yeah. And there will be also questions regarding that. Okay, here are some data. People calculated something. What is the meaning? Remember, this is something we've been also discussing here a lot. Now, somebody is asking, can you talk about the overall grading of the course? I'm decent. Look at the first PowerPoint, I couldn't figure out. Really? Interesting. Oh, yes, I can talk about the, one moment. Yes, I can do that. If this was really not understandable, yeah, then I will do this. Oh, let me just do one thing. Yeah, okay. Yeah, I made some arrangements regarding the test so that it will be set up as we explained here. Find the introductory. If there's no grading here, then this is very strange. So, 2 tests per semester, each gives 10% of the final mark. The exam at the end of the course gives 80% of the final mark. This is the logic. Yeah? Oh, no. And exam will be in 2 parts, theory and practical exercises. I've usually done it like half and half. So one gives 40 and the other one gives 40. But I'm not promising that it will be this. Maybe it's like 30-50 or 35-45, yeah, but in any case, they are comparable. So the exam answers and the ability to solve calculations, yeah, are comparable. And on exam, the calculations will typically not be such that you can do with a pocket calculator. Yeah, they typically need Excel. I mean, they are more substantial, like the ones we've been doing here. So for example, some North test uncertainty or uncertainty of regression analysis, etc. So you need some spreadsheet. That's it. Yeah, I think I've probably answered your question. No. Yeah, it's oral exam. Yeah, this is said here. Yeah. Oh yes, it's speaking exam, if you wish to call it that way. So what how we typically do is that we start with the oral part. You answer all the oral questions. Then I give you the exercise, and then you will have several hours for solving it. But we close the session, and you submit your exam, and I will contact you either this evening or late next morning, etc. when I've checked your work, and then I will give you feedback and then give you your grade, so that you have hours of time for the exercise. And of course, again, you are not allowed to consult with anybody. Of course, I cannot run around dormitory checking who is consulting with whom, so I count on your honesty. So there's actually a lot of trust we are putting in you, that you are honest. But this gives the very nice flexibility that you don't really need to be even in Tartu. I don't need to be in Tartu. You don't need to be in Kemik. You don't need to come to Kemikkum. And we have very large flexibility with times. It can be like, again, Saturday evening, if somebody wants really to do it on Saturday evening, etc. Maybe I'm not so much in favor of Saturday evening, but if it's really needed, yeah, we can. And each of you will have a separate exam time, so that the exam timing will also be ultra flexible. Yeah? I will propose some time slots myself, but then you are all welcome to also propose your time slots, and it will be possible to do the exam until the end of June, so that there's, yeah, you have lot of flexibility. And some of you will start like internship already in June, etc. Yeah? So some of you will maybe leave Estonia. Some of you have come to me that look, when can I count that exams are over, that I can leave Estonia? Then my recommendation would be that rather try to get. Now I'm speaking about each student actually. For each student, if you need to leave Estonia in the beginning of June, for whatever reason, either internship somewhere else or you need to visit your homeland or whatever, then try to do all other exams, certainly, while you are here in Tartu. But this metrology and chemistry, you can leave also for the time when you are back in your homeland, because you can do it from there. I'm not saying that this is like the preferred option. In your homeland, you might not have very good internet in some cases, because you need a good internet, otherwise we cannot manage. But if the internet there is fine, then there's absolutely no problem if the exam is done from, I don't know, Philippines or from Vietnam or whatever other country. But other teachers might not offer you this option, and I guess several, if not most, exams are still written exams where you have to be physically in Kemikkum, and this is then like, take those as priority. And as you've already all experienced in this university, it's up to you to raise your hand. When can we do exam? When will we know the exam time, etc., etc. Maybe beginning of April, slightly too early to start those discussions. But let's say end of April already is certainly not too early. You can already bring up exam timing with other teachers. And here we start exam timing discussion sometime in the second half of May. But here we are not so pressed with time, because again, we don't really need to find one time which suits all of you. Just the opposite. Yeah. each of you have to have separate time. I cannot take 2 oral exams together at the same time because it's individual work. So yeah, okay, I now got slightly distracted, but perhaps that was useful to know this exam thing. Oh, Leib is asking. Effective number of degrees of if it's written effective number of the degrees of the result, this is simply a typo. Effective number of degrees of freedom must it be, and then it is of course done with this Welt-Satterthwaite approach. You tried to underestimate, the results were always low. Yeah, you see, Gleb, this homework has been there for several years. And people have always managed. So I suggest you try to find what the mistake is. It probably is somewhere in your file. If you do not manage, come to me. We can look together. But before that, please take some more effort. Yeah, but thanks for turning my attention. Effective number of degrees of result is just wrong. Yeah, it should not be written like that. I'm surprised that it is written there like that. So, any other thing? Not. Then let us now go to the topic of today's class. We continue with reference materials. And this was the last slide that we saw last time. Any questions about the last time? If not, we will move on. So now, we now will look into the production of certified reference materials. Most of you, most likely in your lifetime, will not be engaged in producing reference materials. Some of you might. But it is useful to know the basics, how they are made, because this also helps you to understand better their usage. Yeah? So first of all, the material needs to be prepared. Then homogeneity and stability need to be demonstrated. And then accurate and traceable values and uncertainties have to be determined. There can be just, let's say, one analyte and one concentration with uncertainty. There can be a number of analytes and a number of concentrations. All possibilities are. It's a complex process. It needs equipment, special equipment and time. And we will mostly look at matrix CRMs. Because, for example, certified reference material, which is just a standard solution, it's not very difficult also. It's not so interesting and useful. This is quite a bit standardized activity. So you see there are ISO standards and ISO guides, yeah, and most of the prominent producers of CRMs these days obey or are compliant with these guides. So matrix CRMs or certified matrix reference materials can be used to different abbreviations. They can be produced as a very large generalization. They can be produced in 2 different ways. One is formulation. Formulation means that you take components as pure substances, put all together and mix very well, and there you have the certified reference material. Then you need to distribute it into small packages or small bottles. Of course, this is possible only with simple matrices. You cannot do that with soil, with meat, with oranges, etc. But this can be done with drinking water, for example. You can prepare very nice drinking water CRMs by taking ultra pure water, And then very pure salts of different metals, like calcium, sodium chloride, etc., so that the ions would be more or less what they are in drinking water. You can put in a little bit of some lead, cadmium, etc., salt also, so that there's also some like small contamination. Well, yeah, and then you have a big bulk of like drinking water, yeah, for which from weighing data, you can weigh those ultra pure chemicals and salts. From weighing data, you can calculate very easily, very accurate concentration. So formulation is good in the sense that it is very easy to determine the reference values. You simply determine them by calculating how much you put in, yeah. And you can use weighing. Weighing is very accurate compared to some trace lead analysis like with ICP-MM. Compared to that, weighing some lead salt, which is of high purity, is much, much more accurate. So very low uncertainties can be obtained. But sadly, as I said, very limited, yeah, because just water, maybe some drinks, oils, in principle, fuels, and then few more. But yeah, not so much. So yeah, calculation from weighing and purity. So because this formulation is really quite limited, we mostly look at the other option, yeah, when you use natural material. Yeah? So that when you, for example, want to prepare a soil CRM, you really need to bring some soil from somewhere, yeah, and then you homogenize and sieve it, and maybe throw away big stones and sticks of wood, plant leaves, and so on. Yeah, make it like homogeneous. Yeah, and then do also other things, which we will look immediately what you need to do. And finally, of course, somebody needs to do the analysis. So the reference values have to be measured with something like, let's say, if it's elements, then it's some atomic spectroscopy. If it's organics, then it's some GCMS or LCMS or whatever analytical technique. So here, the good thing, of course, is that this can be done with any matrix. And of course, you can also do drinking water CRM like that. You take a lot of drinking water, yeah, and then you perhaps still mix and then bottle into small bottles, and laboratories, expert laboratories will determine the reference values. But of course, yes, yeah, compared to formulation, here determining reference values is more difficult and much more costly, of course, because those labs who will be measuring those reference values, they don't do it for free. It's a pretty expensive service, actually. It's not routine analysis, usually much more than a routine analysis. So, as I said, we will mostly look at matrix CRMs that are made from natural material, because this is the most complicated type of CRM to produce. So if we understand how that is done, then everything else is easy. And also, which is useful to already note at this point, we will see later on interlaboratory comparison measurements, where also some samples need to be prepared. And there's a lot of similarity. So preparing a certified reference material and preparing samples for interlaboratory comparison measurements does have lots of similarities. Now, what makes production of matrix CRMs quite complicated is these things here. Let us see. Some of these things are not so intuitive. Yeah? You might not guess. So first of all, it makes any commercial sense only if you produce a large number of bottles or a large number of items or packages or in whichever way they are like stored. It's typically few thousands, like 2,000, 3,000. Because otherwise, the cost per bottle will be so high, difficult to sell. There's a lot of like constant let's put it, lot of constant costs, but increasing the number of bottles does not increase variable costs so much. So those of you who take the economic aspects of measurement, you probably understand what I mean by that. So that if you just make maybe 100 bottles, then it will be extremely expensive. Moreover, if you prepare those bottles and now you have those bottles, then a lot of those bottles you still need to use up for the production process itself. I will show you later on how that is. And this number that you use up for the production process itself might approach 100 actually. At least it is certainly tens of bottles. So that if you prepare only 100, you might end up with just 20 that you can send to customers, because 80 you used up for production, which as I said, I will. Then the next thing, the whole batch needs to be prepared in one go or at one time in one vessel. So, for example, if you take this soil, you cannot do so. Okay, I now have here 20 kilos of soil, and I now will do like 4 kilos now. Okay, process. Now I take the next 4 kilos, and now I process that. Yeah, and now I take the next 4 kilos. No, that is something you cannot do, because then most likely these separate, like batches of 4 kilos, will have slightly different values, and there will be systematic differences. All these mixing, blending, etc. activities should take place in one go, in one bulk. And now suppose it's some kind of meat CRM. It may easily happen that you take, for example, 40 kilos of meat. You have to have a blender where 40 kilos of meat go inside. It's not a small thing on the bench. It's almost like kind of like pilot plant kind of equipment that you need. So in a simple routine lab like we have here, we simply don't have that equipment. So the equipment that has to be there has to be able to process large amounts, tens of kilos, possibly few hundreds of kilos of material, depending on situation. Also, interestingly, every batch is unique because it's natural materials. So suppose you do soil CRM, you bring here 50 kilos of soil, and you do all those operations, yeah, you prepare those bottles, okay, now you have. And suppose in 5 years you have exhausted, you want to prepare that same CRM again. Close to impossible. You can go to the same place, take sort of from the same place the soil, but it will not be the same. All the parameters will be slightly different, so that each batch is unique. And once it's exhausted, it's done, it's gone. You can do very similar, yeah, very similar in the sense that it serves the same purpose, but you cannot repeat it with the same thing. Okay. Maybe questions before I explain this. Nobody has. Okay, yeah, it hasn't really been very complicated. Now, let's see what are the main operations. Now, it is important to note, this is a very general scheme. There are situations when things are not done this way. This is essentially one possibility, but quite widespread possibility. So this is a pretty widespread way how CRMs are prepared, but it's not the only one. So not always they are done like this, because matrix certified reference materials actually is very diverse range of all kinds of materials. So first of all, of course, you have to collect the initial material, clean it, and reduce the particle size and do some initial homogenization. Cleaning means that, again, if you take soil, You throw away roots of plants, some dried leaves, maybe some wood, sticks, all those things will be thrown away. Maybe there are some big, like, chunks of soil, you beat them, like make them smaller, yeah. And do some initial mixing and homogenization. And now it can be different ways depending on what it is. If the analyte and the matrix are not delicate, some let's say minerals, some geological things, also soil for example, soil for trace elements, yeah, etc., then you can use like somewhat harsher conditions. But if the matrix or the analyte is delicate, then you need to use more delicate conditions. Typically, when it's about elements in some quite robust matrix, then we go here, this blue route. But if it's organics, and especially if it's something like bio, etc., in some tissues, meat, etc., then people go this green route. So first, like, thing after this initial processing is some kind of drying. Not all CRMs are dried materials, but the majority of them are. So, for example, you don't really find much milk certified reference material, but you do find a lot milk powder certified reference material. Also, like, for example, if it's about meat, about fruits and vegetables, or like plant leaves, all those CRMs you can find, but most of them are dried powders. And soil, of course, yeah, in most cases can be just oven dried. Yeah, it's spread like more or less evenly, yeah, and dried in oven. If it is mostly elements that you need to determine, elements cannot decompose. The lead atom does not fall into two pieces, yeah, under heat. No problem with that. And lead and most elements also don't evaporate under. These delicate matrices, organic, bio, etc., are managed by freeze drying. Freeze drying is something which you do at low temperature and in vacuum. And the other word is lyophilization. Maybe some of you have is even more familiar with that. Let me put that also. Lyophilization. Okay, can anybody guess why drying is so central, so often so important? One very concrete reason. What makes drying beautiful? Exactly. So life is an amazing thing because it can take place in under almost any conditions, under almost any temperatures, radiation, toxic chemicals, etc. The only thing that life just sort of cannot really tolerate is dryness. So if there's no water, there's no life. So that bacteria cannot really start growing as long as this, or bacteria or other microorganisms. Yeah, it's not. For this reason, most CRMs are dried, not all. Yeah? Most of them are. Next thing is particle size reduction. It is quite important that the particle size is small and uniform. And this is, again, for a good reason. The CRMs, even if they are solid, yeah, as you'll see now, we mostly now speak about solid materials. Again, with drinking water, it's all much simpler. There's no such problem as homogenization. Yeah? But now, if we speak about solids, particle size has to be small because that solid has to be more or less homogeneous, as much as a solid can be homogeneous. So that if you take with some kind of spoon some amount of material, the particles should be more or less like equal, and there should be more or less equal probability of any particle being inside your spoon. Pretty important thing. It has been found out that the best particle size is medium diameter, something like 0.3 millimeters. That kind of an empirical finding. If it's above that, it tends to be quite big, yeah, and then it's homogeneity not so easy to achieve. But if it's below that, then its specific surface, so surface area per mass, becomes increasingly very large. And why might large specific surface be problematic for CRS? What do you think? Could you send to Golam the microphone?
Will it be, I mean, dusty or?
Yeah, and what's the problem with that? Yeah.
Flow properties will be affected, I guess.
Yeah, that also actually, yeah. But there's one more thing. What property will very much increase if material specific surface becomes large? What ability of the material to do? Sorry? Both are sort of on the right track, but not exactly. Huh? Yeah, okay, yeah. Let's say the reactivity is Gleb is saying hygroscopicity. Yes, this is also very well said, but let me put in a more general ability to absorb any kind of things onto the surface. And ability to absorb water, of course, is particularly important in this context. So there's then the danger that, okay, you take it out of the bottle, you put somewhere for weighing, and during that time already it absorbs moisture from the air so that you get the wrong mass. Yeah? Also, please note, freeze-dried or lyophilization, so lyophilized materials are oftentimes very hygroscopic. So they literally suck water in as soon as they are in contact with air. And to minimize that, the specific surface should not be very large. Okay. The next thing is sieving. Sieving, the main idea behind sieving, of course, is to make particles as uniform by size as possible. Why is it useful to have particle size uniform? Okay. Has anybody of you ever tried like this? That when you are on a beach, for example, I think that might have happened when you were a child. You take a small bucket. Now you put in small sand particles, but then bigger stones and maybe big stones, smaller stones, and then a lot of sand, more stone, yeah. Put all those different small and big, and now you simply shake it like this vertically, yeah, so that they will jump in. What will happen?
We will find the smaller ones collected at the bottom.
Exactly. They will be pretty well segregated by size. Big ones on the top, small ones on the bottom. And now, depending on the properties of the material, it is very much possible that the composition of those big and small pieces are on an average somewhat different. And if it's then segregated, and if you send it to the customer and the customer gets a bottle which has gone through transport. Yeah, transport almost always involves some vibration. Yeah, and if then the customer gets the bottle, which is to some extent segregated, then it can happen that on the top, the average composition is slightly different than on the bottom. And for that reason, it's good if they are as similarly sized, those particles. And sieving, of course, can organize that. Yeah, you can have different sieves with different mesh size and get just the particles that you wish. Obviously, during all this procedure, quite some material will be lost. Yeah? So that this even more reinforces what I said, that you need oftentimes tens of kilos, possibly hundreds of kilos. And now you have this sieved material, and now you still need to homogenize. Now it's like, let's put it, the final homogenization. Now it's already dried and particle size uniform. But still, now it has to be mixed very well, possibly using all these I think, okay, Koit-Herodes has also to Estonian and also to each students, you all have been to Koit-Herodes lecture where he has explained the sampling equipment. Yeah, that there are, for example, equipment where you pour in and which divides into different like streams, and then you can simply like pour it into one big pile, and then you take the quarters out, and then you again. So all those things can be used depending on situation. Of course, it's very hygroscopic. You cannot do it on air. Yeah? You can have to use some glove box or something, and so on. But in any case, this big amount of material now needs to be somehow homogenized. Let me see. I've neglected the chat. Yeah, Komal, you said very correct thing. Yeah, sorry, I did not notice. Gleb is saying, sieving doesn't make sense to me. Do we assume that different fractions are of the same composition after sieving? Or how the sieving proceeds? You see, Gleb, we get different fractions, but our aim actually is to get just one fraction, so one average particle size. The others we either throw away or we like treat them again to further reduce the particle size. Now, if I look here, yeah, I would expect there's for 10% of bigger fractions may have different. Yeah, I don't so well understand your last comment, but perhaps it is helpful that if I simply say that with sieving, they take one fraction that they need. Too small and too big will be thrown away. Or will be reprocessed, yeah, depending on situation. One fraction is good enough because it has the most uniform particle size distribution. Now, okay, yeah. All right. Now, homogenization, yeah. Now we have some big pile of this, and now it needs to be bottled. Yeah? Bottling means that, okay, it can be really bottles, but it can be also all other kinds. It can be ampoules and some plastic bags and so on. So there's different ways how to package. Finally, this slide ends with huge number of bottles, or huge number of packages, which are supposed to be identical by their composition. The whole idea is that all bottles are the same. They are never completely the same, but as close as possible. Now, let me ask this question from you. For example, I said that, okay, meat CRM oftentimes is a powder, lyophilized or we freeze-dried meat powder, and the same goes for, say, fruits and vegetables, oftentimes. But in real life, you analyze meat, which is this slimy, like meat, yeah, like meat is. Is that the problem? And what can we do against that?
Yeah, that could be a problem with matching because CRM takes out less moisture than the real sample. And sometimes there are CRMs that has instructions to reconstitute the CRM, meaning to reintroduce what was lost to the process. And sometimes, if I'm not mistaken, the reported value of the material is with the reconstituted samples or CRM than the dried ones, but it is the case basis.
You are speaking as if you work in CRM production. This is exactly that. Yes.
Because yeah, I did.
Ah, you have?
Yeah, in metrology of the
All right. Which CRMs did you prepare or participated in?
I'm mostly involved with the inorganic and inorganic reference material, so trace elements in drinking water, in we have sugar. There is
All right. Good, good. Very good. Oh. So indeed, in many cases, when you get this kind of CRM, you need to read carefully what is written on the certificate. We will later on look at one of those certificates. Certificates, very important. It tells you how you really have to use it. And in many cases, you first need to add water, yeah, or you weigh some portion, then you add water to bring it like to a similar consistency with the real material. And only then you run it through the sample preparation process. So that, yes, it does make some matrix differences, but in many cases, this can be like rolled back in the sense that you simply add water and as Christian put it, reconstitute the original material. This scheme comes from the European Commission's formerly Institute for Reference Materials and Measurements, and now it is called JRC GALE. JRC stands for Joint Research Center, which is the European Commission's scientific arm. And GALE is the name of the place in Belgium where that institute is located. Why I'm mentioning this here, because the next slides also come from this JRC. They're quite old. You know? I don't have good newer photos, and I think just for illustration, it's still very, very good. So here you see one piece of a blending equipment. Yeah, this is actually a mill. Yeah, which can mill things, and as you can see, it is not a small piece of equipment. It is huge actually. And this is here cryo mill. For example, meat cannot be milled. You cannot because it will be all over the place. Yeah, so such materials as meat can be milled at very low temperature when they become brittle. This is oftentimes achieved with liquid nitrogen, and as you can see here, this is exactly what they are. This here is a glove box. As I mentioned, after freeze drying, materials can be very, very hygroscopic. You cannot handle them on air. You have to use inert gas glove boxes where it can also be not maybe inert gas, it can be simply dried air in some cases. Yeah, but in any case, you have to have such equipment. And again, you see it's not small, big. So you cannot have very small. And here you can see how a person is working inside that glove box. So it is gloves through the wall of the box, yeah. And here the person is right now, it seems, doing some sieving operation. Here is a vacuum oven. Yeah. Here is some mixing equipment. Yeah. Here I have the critique that this is like separate 3 bottles. It should be in one bulk, but probably this is something, let's say, preliminary, so that later on it is mixed like in one big set. Then this is here ampuling line, which seals glass ampules. So ampules are not so convenient to use, but they are very good for storing, because like if ampules are sealed in good way, and this machine does it fairly well, yeah, then the ampules are like absolutely safe from the air. Yeah, so air simply cannot get in any way, while into like original bottles, still through the cap, the little bit of air always can come in. And this is some bottling line. You know? And here are now simply some examples what CRMs might look like ampules and this kinds of vial bottles. You know? And this is also very instructive. If you look carefully, you see there are many meters like going back to the room. So this is a huge storeroom. And this is also something that you need to have if you want to produce CRMs, because as I explained, you need to produce a lot of bottles at the same time, but you cannot sell all of them at the same time. You may be, once produced, you will maybe be selling them for 10 years, and you have to have some place for storing. And this can be even more complicated because some CRMs need to be stored in refrigerators. Some of them need to be stored in freezers, so that you have to have huge refrigerator rooms and huge freezer rooms, which all is costly to have, costly to build, costly to maintain, consumes electricity, and so on and so forth. So all these things make CRM production not really a good business. So there are not so many organizations which produce matrix CRMs purely on commercial basis. The same IRMM, yeah, which now is JRC Gale, is a big producer. Yeah, actually it's now maybe less, but it used to be a very, very big producer. But that's a European Commission. Then another big one is NIST, NIST, the National Institute of Standards and Technology in the USA, which is a governmental institute. Then LGC, the Laboratory of the Governmental Chemist in the UK, which is the that one is not governmental. It's a limited company, but it still gets huge funding from the government. Yeah, it's operated as a private enterprise. Yeah, but it's still it's owned largely by the government, and government also government. As it's a private company, government does not just give it to it money. That just doesn't work that way, but it has government contracts for doing it. Still, it's a private company, but has good relations with government. Yeah, it has been actually originally set up by the government, and government still orders or contracts certified reference. Now, Gleb is asking. I also wanted to ask exactly that. I would guess if you do meat analysis, you have to dry it, or at least you have to know it's old already. Yeah, very sorry, Gleb. Yeah, I missed your message at the right time. But do you still have some standing question, or have I managed to answer your questions already as I've been going? Gleb, I'm coming to that. Or perhaps I can very quickly answer now that usually we can. Okay, let me. I don't like to not answer questions, and let me take for a moment this file. This is the CRM certificate. Oh, wait. Yeah. This is a sample CRM certificate. We'll come back to it later on with more detail, but right now I simply want to give the general thing. So here we have the uncertainty, yeah, which is 29 nanograms per gram. And if you now read down here, you notice that it's expanded uncertainty with coverage factor K2 according to height of the expression of uncertainty measurements. This is this isogam, yeah, corresponding to a level of confidence of about 95%. So this is like very correctly put. You know exactly what it is, okay? If it obviously has a large number of degrees of freedom, yeah, because otherwise K2 would not correspond to 95% probability, average probability. And if you divide this by 2, you will get the combined standard uncertainty, which you can then feed into any of your uncertainty calculations. So very often, this is how CRM certificates present uncertainties, and this is the proper way to do it. When I explained that, yeah, routine labs oftentimes simply put K2 and don't say anything about coverage probability, then CRM producer is not a routine lab. It's much higher level and like should be much more rigorous with presenting things. Sometimes CRM producers also don't explicitly say this 95%, but almost always you can assume, if it's a like respected prominent producer, you can almost always assume that there's far enough degrees of freedom and you can handle this as a 95% coverage probability. Kleber is happy. Yeah. Okay, good. Yeah. Then let me go back. Okay. Now we come to the reference values. So establishing reference values. How is that done? We already looked at the two main situations here. The first was formulation, yeah, when you get the reference values from weighing and volumetry data. See? And the second one, of course, is when it's not formulation, but real material. And then what people do, they make the CRMs, yeah, the bottles are made, and now they are analyzed. And if possible, the reference value is determined by a number of labs. I have written here several, but it's sometimes around 10, which is a lot. Number of labs, and it is very useful if they use different techniques. For example, if it's trace elements, it's very good if some do ICP-MS, some do ICP-OES, some do maybe neutron activation analysis, etc. So that is different ways. Why is that good? You see, especially those of you who have taken the atomic spectroscopy course, you perhaps remember that, for example, ICP-MS has numerous interferences like isobaric interferences, and then there are all those polyatomic interferences, yeah, with argon complexes with everything, etc. And if everybody does it in the ICP-MS, then in principle, the interferences are the same for everyone. All of them might get slightly higher than they should, and the value would be biased. But if another person does neutron activation analysis, which is a completely different technique based on completely different logic, then it works completely differently. Another one does maybe ICP-OES, etc. And it's essentially an interlaboratory comparison measurement. Yeah, ILC stands in this lecture, in this course, for interlaboratory comparison measurement. That will be our next topic when we finish with CRM, and then we will look at that like once again. But right now, let me simply say that if you have now all those thousands of bottles, then what you do, you contract those different labs, you know, and send some bottles to every lab. Usually you don't send one bottle, several. Every lab gets several bottles, and then makes the analysis. Nobody knows what the true values are. Like fair play. And then they all send their results back, and then some data analysis is done. Okay, how well they agree between themselves. Also, I have some examples about that. Okay. Now, as I already said, if it is possible to do formulation, then weighing data can be used. Simple and cheap way to get reliable reference values. But of course, large amount of material, homogenization is critical. Yeah? With drinking water, homogenization very easy. Also, you can do that way in principle, seawater reference material, etc. Yeah? But yeah, and also maybe some oils and things. But nevertheless, yeah, only with relatively simple matrices you can do. And now, if it is done by measuring, so that you cannot do formulation, then this is what you need to do. It is mostly, as I said, interlaboratory comparison measurements, only expert labs. So this is not an ILC where every lab can participate. Preferably different techniques, as I already said. Here is another example. If it's polyaromatic hydrocarbons, this PAH, polyaromatic hydrocarbon, then some do this by GCMS, some do it by LCMS, and also LC with fluorescence detection. Very good if all those are represented among the Every lab typically gets several random bottles. And this is actually, again, an important thing. What random means? If those bottles are filled, it's called something like filling run. Some huge bulk, and then either some machine or whatever it does, every bottle gets the material, and then those bottles will be moving. They are all like in sequence. Oftentimes they are all numbered so that they have numbers. And you don't give to one lab 3 consecutive bottles. Instead, you take one here, so one can carry like number, let's say 37. The other one be 156. The other one will be 279, etc. So you get bottles like from the beginning and from the end. Again, to take care of possible segregation in this big bottle, so that the first bottles that are filled get slightly different composition than the last one. Also, quite important bottles in this filling run are the first ones and the last ones. The first ones and the last ones never are sold. They are usually included into the between bottle variability study, so that this is also something that has to be done. I'll come to that. So although those labs sort of determine the reference value, but in addition, either one of them or the main organizer will also need to do some other determination, like this between bottle variability, which I'll come to and explain also. So that lots of bottles are needed for the analysis. Not so that, okay, we need one value, okay, one bottle. So look, it doesn't work like that. Okay, then labs send results back and some kind of consensus is then attempted to find. I will later on have some scheme that finding the consensus might not be so easy sometimes. And this consensus value is then used as the reference value. And the uncertainty of the, let's say, analysis has to take into account disagreement between participants. And there's a technical discussion. So it's not done just on the basis of statistics, but on the basis of technical discussion. Now, these reference values of certified reference materials always, of course, have to have uncertainty estimates. What that uncertainty needs to cover is the uncertainty of the reference value indicates the range within which the true analyte content is, and now come three things, in any of the samples, withdrawn from any of the bottles during the entire shelf life of the CRM. And that shelf life is years. Sometimes can be 10 years, sometimes can be 20 years, sometimes can be less. Yeah, but so that the uncertainty range has to cover from like the first bottle here to the last bottle there, the first one used today, the last one used in 10 years from now. All those variabilities that can be either by between bottle variability or maybe changes in time, etc. All that has to be covered by this. This is sometimes not so well understood. So please raise your hand who thinks that you understood what is meant here. So you see, this uncertainty is like quite a demanding thing. And also, if this work is not done well, homogenization and stability, then what can easily happen is that you have so wide uncertainty range that the CRM is of very limited use, yeah, because if the analyte content that you read on the certificate is, let's say, 100 milligrams per kilogram plus minus 70 milligrams per kilogram, and you are not happy really to buy this CRM, then people will not buy it, and it will be commercially even more disaster than it. So this is why they need to put a lot of care into all this homogenization, because otherwise uncertainty will be so wide, it will be very, very, very useful. It's also the sad thing that you cannot correct this afterwards. So if you've done something wrong in the beginning, afterwards you cannot go back. Yeah, you simply have to like admit what you have. Okay. Now, since uncertainty has to cover all this, then the uncertainty has to take into account all those things here. So first of all, uncertainty of the analysis itself. Then between bottle variability. Then possible inhomogeneity within one bottle. And possible instability. Now, you've heard from me the word possible many times, yeah, in this course. Let me now ask you, in this case, what is the meaning of possibility? So possible. Why have I written possible there? Gleb, you say the possible means the same thing as meant with bias. Could you be more specific? What is it then?
So it indicates that we may have some instability related issues with this specific sample, but it doesn't specifically have to be unstable. It may be perfectly stable, but we have to act as if some instability was present in order to make sure our uncertainty range is big enough.
Yes, correct. So again, it can sometimes be very difficult to actually find out whether some variability is caused by instability or not. So that the uncertainty simply takes into account possible instability of the. And here is the typical formula that is published, or that is used for this. Analysis uncertainty, then variability between bottles and within bottle homogeneity, and instability. This is also, of course, important to note that this actual calculation might even be slightly more difficult because, for example, the uncertainty of analysis might already include some part of variability. So it might be more tricky, but we will not go into very deep, deep discussion here. So for us, these uncertainty components, we keep them as they stand. Now, Gleb has asked, how do they secure shelf life? Are additional analysis performed regularly? This is a very good question, Gleb. If I can, I would postpone it to the moment when the respective slides come. I will then explain there. This all will be in slides. Yeah. Now, if we speak about this UANAL or analysis uncertainty, can be quite tricky because there are several labs. The results almost always differ. Yeah, there were different techniques, so that they all produce some results. They all have their own uncertainties, and those results and the uncertainties do not necessarily match. And in this kind of interlaboratory comparison, labs are typically not excluded on statistical basis. They always try to find what might be the reason. You can now see here how it can be, for example. So, see, labs here, yeah, the results and their uncertainties. It's K2 uncertainties in this case. And now we see that two of the labs are specifically higher than all the others. And if the discussion really gave the result that, yes, okay, we find there are some interferences, yeah, which led to increased results, then the results can be excluded, and then this uncertainty range is pretty okay. And the reference value, I'm right now, this is like a simplified thing in the sense that I'm at the moment not considering the bottle-to-bottle variability and instability. Yeah? The reference range of this analysis is like this. Suppose now that these results are just as good as anybody else, then they actually cannot really. Because it also is possible that these people lost some of the analyte. Yeah? They had some losses. And then what they typically would do, they would increase the uncertainty. And of course, here they are not so happy. Yeah? I've written here not very successful. Yeah? Because the uncertainty range now is quite wide. Yeah? The K2 uncertainty now is more than 10%, which is not really so pleasant. You still can use this CRM and do some things with it, but some things you already cannot really do. Yeah? So, for example, if some lab wants to test like some very close match or mismatch, then this CRM doesn't really work because it's its own uncertainty. Now, if we now speak about bottle-to-bottle variability, inhomogeneity, and stability, what people do here is, if we speak first of all about variability between bottles and inhomogeneity within bottle, people take a number of random bottles, and most of the time the first and the last are also included, because it is likely that the first and the last might be somewhat more influenced, so that in order not to like underestimate uncertainty. No? And in the case of stability, what usually is done is something like artificial aging. And this is actually, the stability is actually the most difficult part. Because if you really want to test whether something is stable for 10 years, then the only like rigorous way would be to wait 10 years. But it's something that CRM producers absolutely don't want to do, because then they cannot sell anything until 10 years pass. This is commercially just absolutely ridiculous and absolutely doesn't work. So that what people do, they do artificial aging, and also oftentimes they use their experience. So for example, if it's some grain CRM and they've been producing grain CRMs for decades, then they already know how stable or unstable they are, so that they don't need to do so careful examinations every time if the grains are just very similar to what they have been in the past. Also, the same goes for all kinds of minerals or maybe metal alloys, etc. For example, if it's some metal alloy pieces in a bottle, really nothing. Yeah, so some types of CRMs are not really very troublesome in terms of stability. But of course, anything related to food, bio, etc., is very, very, very delicate. And how artificial aging works, I have the next slide for that. And now variability and stability analysis is always done under repeatability conditions. This is, I have a typo here. What does repeatability conditions mean? What does repeatability conditions mean? We've spoken about it. Could you take the fact? Yeah, everything on one day using the same calibration graph, the same instrument, etc. So, like you put all your things into the same autosampler and program. So that if you do this variability in homogeneity study, then for example, you could do it as follows. You take 10 random bottles, and including the first and the last. You take maybe 2 subsamples from every bottle to account for within bottle variability. So you have altogether 20 samples. Now on the same day, you do sample preparation with all of those. You put everything into the autosampler, yeah, and now you run this whole sequence, and next day you come back and you examine how much those values are variable. My next question to you, do we need to worry about bias in this kind of, let's say, variability in homogeneity study? Is bias a problem? Interesting. I was expecting very fast answer here. What he wants to say. Is bias a problem? People on the internet, please also jump in. Gleb says no. Any other opinions? Okay. Who thinks that bias is important? Who thinks that bias is not important? It's not. Interestingly, we only need to have differences between bottles. All of them are higher or lower than the real value. Not really a problem. This higher or lower, this is taken care of by these labs. So for them, bias is extremely important. They must not be biased. I mean, individual labs might be biased, but this whole, let's say, bunch of labs or this collective of labs must not be biased. If one is biased this way, the other one should be biased that way. So if their average is biased, this is very, very bad. But for homogeneity, variability studies, bias is not an issue. But for this aging study, what do you think? Is bias an issue there? Why? Interesting. Okay, let's postpone that question until we have discussed the next slide. Okay, so here now, Gleb, I'm coming to your question. Yeah? So this is now how this instability would be tested. And this figure comes from the same certification report that is provided also for you as sample in Moodle. Yeah. And this comes also from this JRC. Yeah? So the Joint Research Center has produced this. So what they do, they keep some bottles, and I see here, if I'm counting correctly, in batches of 3 at different temperatures. First of all, here they examine at plus 18 degrees, and we can be fairly sure that here indeed the content decreases. Now the analyte is acrylamide here, but that's maybe not even so important. So here the content clearly decreases. Here it stays more or less the same, and here it actually seems to sort of increase. But if you look at the variability of the data points, you see that there's almost no trend. Yeah, so this slope does not really have any. They store, so all these temperatures are like temperatures at which decomposition might occur, but they additionally have a reference temperature. Reference temperature is -70. And this is pretty widely assumed and accepted that even the delicate bio things, -70 is sufficient to preserve. There are also few things that you have to preserve at liquid nitrogen temperature. That's like very few. Usually -70 is perfectly okay. And there are freezers which provide -70. And this is like some reference samples are put at -70 degrees into that like reference freezer, where they assume that nothing happens. And now, important, this analysis also has to be under repeatability conditions. It's sometimes called isochronous stability. But now, hey, wait a minute, yeah, there's months, yeah, 16 months, 18, blah, 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 blah. How can you do that under repeatability conditions? Any idea, anybody? How is this study performed? Yeah, like technically. Christian, you have maybe done it yourself.
Yeah, I actually under repeatability condition, suppose although it will take several months, yeah, but it is assumed that the same techniques, methods, and of course because a lot of time passed, you may change your reagents and so on, but the idea is that you do the same method from the time that you perform, for example, the homogeneity. What method is that? It is on the procedure. You should also do it under this instability test. Yeah, it's like a supposed repeatability condition, even though we both know that some factors might be different at that time, and that could be a factor of reproducibility. But yeah, it is quite assumed that what you did from the first 0, let's say if it is a result of homogeneity, you do it the same thing as the other months.
Interesting. Yeah. This study can be done at truly repeatability conditions. Not assuming, but truly repeatability. Using this thing, yeah? Anybody guess how?
Okay. All right. I remember now. Isochronous means that you put bottles two at a time in a particular intervals, and at the end of for example, 24, all of that group of bottles will be analyzed under the same repeatability condition. I remember now.
Exactly. Yeah. So, for example, this bottle spends 24 months at plus 80. This bottle spends at plus 18, 16 months. Then it's put into minus 70. Or it might be in the minus 70 freezer for the first 8 months and then spend the remaining 16 months, whichever way you want to this logistically organize. This bottle spends 8 months at plus 18 and then is put into minus 7. And these bottles sit at minus 70 all the time. And exactly the same is here. So when 24 months pass, some of your bottles are still at minus 20, minus plus 4, and plus 18. So these last ones, yeah. All the others are sitting at minus 70. Then you take all those bottles up, warm to room temperature, open all, make all sample preparation, put everything in auto sampler, and run in the sink. So it is possible with the help of this reference temperature where you can be sure that nothing changes. It is possible to run this under repeatability conditions. And this is exactly what is useful to do. I would say it's almost mandatory to do because those changes can be extremely subtle and small. And if you do this now and the next analysis at 8 months from now, you cannot catch those small changes. So repeatability conditions absolutely must. Please raise your hands who think that understood how isochronous study can be done. Good, very good. People on the internet, do you also? Okay. Almost everybody understands. Yeah, very good. Gleb, I'm coming back to you. You say, I can't answer since I have no idea how our aging studies perform. Did I now manage to explain how these things are done? Good. Yeah. Okay. So this is about producing certain. Yeah, please. Yeah, take microphone. Yeah.
Quick question: is the reference bottle in a 1:1 pairing with the aged samples so that we won't have the instability due to freeze-thaw cycles?
So now, some freeze-thaw certainly will happen. Now, you cannot avoid that. The problem is that at least like these bottles here certainly have to be sitting at minus 70 degrees for a long time, and most other bottles also. But it is not many freeze-thaw cycles. It's just put in freezer, taken out. So it's only one freeze-thaw cycle. Yes, I understand what you mean. In some cases, that might also cause problems. Luckily, if it is a solid material, dried solid material, then usually it's less problematic. It's like more problematic if it's water-rich material. Then indeed, since water expands on freezing and then contracts, then it might break some molecules. So yes, there might be freeze-thaw issue problems, but this is the logic how most of those stability studies are done, and probably then it's not a big problem. Sadly, I'm not educated enough to very to answer you in a detailed way. Okay. Gleb is asking, I have a question about biosamples. Sometimes people are concerned by freezing because ice crystals. Yeah, okay, yeah, this is very much like what Hans just asked. How is cryomilling and everything related to homogenization delicate enough so that important properties are preserved and are comparable to real biological samples? Do real biosamples have to be homogenized as well? Yeah. So let's see if first of all, if it is all those cryomilling, etc. operations, even if some of the analyte is decomposed at that time, it's not such a big tragedy because analysis is done afterwards. So the analysis will be done already with that freeze-dried sample, or it might be possible reconstituted freeze-dried sample. So that if in the past, during cryomilling, something broke, then that will not really influence later on. What indeed can happen is that this cryomilling, etc., can break some tissue at that stage, true. But then again, after freeze drying, I would say that then freezing is probably not going to make or break the structure very much because there's very little water left. I'm not sure, Gleb, I managed to answer. I also don't know so well the specifics of the biosamples. But in any case, these are the approaches that are used also for biomaterials. Let's say food reference materials, which are bio also. All right. So, yeah, Sarah, please. We do only one analysis after 24 months have passed. We take all these into like one big batch, into one run. These last ones are certainly at those temperatures that are written here, but these here might by then be already at -70. So everything will be collected, yeah, and brought to room temperature, then all sample preparation done at the same time, and everything is analyzed at the same time. Yes, this has to assess the stability and the assumption, and yeah, as you can see, this assumption really turned out to be true. The assumption is that the longer you keep something at +18 degrees, the less analyte you will have there. And here you see it really is the case. So +18 degrees centigrade is not a suitable temperature for storing this sample, yeah, because the analyte content will change. That's so small numbers. Yeah, from average, let's say 420 nanograms per gram to an average 380 nanograms per gram. So this is quite a big change. So yes, it provides that information. Yeah, Ola? Could you take microphone?
So then when you conducted this study, you didn't know what is not a suitable temperature for storage. Then when you're accounting for uncertainty, do you also account that some places might not store it properly, and then you include like all of that into uncertainty, or you only include like assuming like proper storage conditions?
Yeah, uncertainty is always given assuming proper storage conditions. There would be no way to do it otherwise. You know? So that from this study, from this stability study, people get the information how they should store this CRM. We will see later on in the certificate. I don't remember right now. I think it is suitable. It is considered suitable to store it at +4 and not at +18. I think -20 was not required. We will see later on. Yeah? And yes, the uncertainty assumes that the customer has stored. I see Gleb is writing something. Let's see what Gleb says. While Gleb is writing, let me say something. Irja has programmed your test, so it opens at 13th of April, 5 o'clock p.m. and it closes 13th of April, 21 o'clock. And 1 hour, 30 minutes is the time. So it is now already programmed in Moodle. So don't forget on Sunday to do it. And now Gleb says, I got one more aging related question. You said in the beginning that in order to guarantee 10 years stability, you have to wait for 10 years. Yeah. No, I said that fundamentally, rigorously, you would have to, but nobody does that because they don't have enough. So it just does not work. Moreover, if some CRM is produced, it oftentimes is done because there's some need, somebody really needs it, and that need cannot be postponed to 10 years. So, 10 years? Do we just then do 2-year study to extrapolate to 10? Yes, we do 2-year study and extrapolate to 10. I don't remember what exactly was the shelf life of this CRM. We will check that next time. Yeah? But yes, usually they do like, let's say, artificial aging, like this plus 18, yeah? This artificial aging at somewhat higher temperature. Then they store, we ask the customers to store at lower temperature and write the shelf life as a longer time than just 2 years. Although 2 years, not too bad, actually. If some CRM is for which there's a lot of demand so that people buy many bottles all the time, then it makes sense also to actually have a shorter shelf life so the uncertainty can be more exact, more well-known, and simply make new batches, yeah? If you can sell many bottles already during 2 years. But most of the time, it's the problem that you cannot sell them very fast because people from the street do not buy CRMs. Yeah? It's only labs that do that respective analysis. But there are not so many customers for CRM production compared to production of, I don't know, washing powder or toothpaste, for example, which everybody buys. So let's see. We actually already quite a bit over time, but I still want to wait what how much can you extrapolate? Claire, could we come back to this tomorrow? Tomorrow we will take the certificate and the certification report, and we will check how that was done with this specific CRM. Yeah? No, don't need to be sorry. Just the opposite. I'm very happy for your interest. Yeah? It's good that this is a topic that is of interest. So, but now, unless some quick last-minute question, we close here. Yeah. So, thank you. And we meet again tomorrow.